As the title indicates, the topic of my talk remains in the frame of the first talk. This is a coloring talk, but it will also be a packing style, so it will be related to independent sets and larger packings. This will be, in a way, half of survey talk to give you an impression what has been done in the area. And in the second part, I wish to go to two recent topics. Well, everything is relatively recent if you compare it to list colorings. But in the second part, it will be very recent. So there were a couple of breakthroughs just a couple of months ago related to subcubic cases. And finally, I wish to give you some open problems which will naturally come out from the topics I will cover in this course of the talk. So first of all, let me define you the packing coloring concept. What is an I-packing? An I-packing is simply a set of vertices. So we define now an I-packing. This is the key concept we need for this talk. And what we want is that you have a subset of vertices such that vertices in the subset are far away enough. When I is prescribed, you want to have that each pair of vertices at the distance at least I plus 1. So the distance should be more than I. Which means in the particular case, if I is just 1, you will get simply a usual independent set. Okay? So what is the coloring? Usual vertex coloring of your graph? Well, this is simply a partition into one packings. Now, in packing colorings, we want to partition into different packings. So we say that the packing chromatic number is the smallest number k, such that you can partition your vertex set into sets x1 up to xk, where xi is an I-packing. Okay, so this is the key definition. So what you want is x1 is simply an independent set. Then x2 is the usual what is called packing. So if you only say packing, this is a set of vertices at distance at least 3. So this terminology comes from coding theory. If you want to have perfect codes, you want in graphs, then you want to have vertices to be at distance 3, and the closed neighborhood should cover your whole vertex set. And so on, and if k is the smallest integer, positive integer, such that you can make this partition, then this is the packing chromatic number. Now, okay, these sets, I mean, some set could be empty in principle when you do that, but if you really do optimally, then there will be no gap inside, because if you use color k, then color L is not used and L is smaller, when of course you can forget about color K and you color every vertex with color K instead. You prefer color L because the distance condition will be even stronger fulfilled and you will get a better packing coloring. So this concept was introduced, I said it is not that old as list colorings, but it is now relatively mature area. So it was introduced, well, the paper was written in 2004, the seminal paper by Wayne Goddard, Hedit Niemis, and Harris. But the paper was actually published only 4 years later. And even before the paper was published, the original name, which was broadcast chromatic number, was already changed. So actually we came together with Roll, he's also here, a couple of years after this paper was written, with the second paper in which one we suggested the packing coloring terminology and also this notation chi sub rho, and this is now used all the time since then. So the original motivation, so if someone would like to get some motivation, the original motivation for this concept was the frequency assignment, and the reason for the original terminology, broadcast chromatic number, was just this motivation. But as I said, in these days it is now packing chromatic number. So before I go on, let me just give you a few simple examples just to get a feeling, just to get a touch of the concept if this is new for you. So first of all, let's consider some very simple examples, paths and cycles. And then we will go maybe to a little more complicated, let's say simple examples, trees. But we will come back to trees a little later. So what can you do with paths? Well, first of all, it's easy to color P3 with two colors, 1 to 1. So you have these two vertices at distance 2, so they can receive the same color, and you can color with the middle vertex. What about P4? Well, here you already need the third color, because if you use only two colors, you need to start like that. So this is the only way how you can use three colors. But now you see that this last vertex requires the third color, because it cannot be 1, and it also cannot be 2, because 2 is too close. This vertex colored 2 is too close to the final vertex. So you need three colors. But now you can just repeat this pattern. This works now for arbitrary paths, so you just repeat this 1 to 1, 3, 1 to 1, 3, and so on. And this tells you that the packing chromatic number of paths is 3 for any path except the P3. And it's similarly for cycles. The 3 cycle, of course, needs 3 colors. Clearly, the packing chromatic number is at least big as the usual chromatic number. And if you use this pattern and you round around into a cycle, this will work if the cycle will be, the order of the cycle will be congruent mod 4. So you just go around 1, 2, 1, 3 around, and if it's congruent mod 4, then this will work. And otherwise, you will need the fourth color. Another simple situation is for the packing chromatic number 2 and 3. Well, for the packing chromatic number 2, you get only stars. And for packing chromatic number 3, you can characterize all graphs which have packing chromatic number 3. Here is the statement for two connected graphs. I will give you in a second general statement, but this is nicer formulation, so that's why I wanted to put this separately. So in the two connected case, you can color with 3 colors precisely the graphs that are obtained from bipartite multigraphs when you each subdivide each edge once. So you have multigraph, you can have multiple parallel edges, because when you subdivide, you get a simple graph. And the idea behind, so why you can color with 3 colors? Well, the idea is that the new vertices, the subdivided vertices, will get color 1, because they will form an independent set. And the original vertices, when you subdivide it, so if they are in the same bipartite set, they will be a distance at least 4. So before they were a distance at least 2, now they are a distance at least 4. So one bipartition set can be colored with color 2 and the other one with color 3. So you can color with 3. In the other cases, you just take a join of an edge and an independent set, so a very special split graph. You can do the same for the general situation if it's not too connected. So then you have a little more technical condition, but it's also easy. So you have some, again, same situation. You start with a bipartite, multipartite graph. You subdivide some edges, and you can add some pendant edges, and you can also add some t-add, whatever it is. It doesn't matter. So let me give you some general upper bounds first. This is, of course, the case. So the concept is well defined. This upper bound in particular says. And if you do the following, if you color the vertices in the largest independent set with color 1, and you color all the vertices that are remaining each with separate color, you will get a packing coloring. And if you just use the bound that the independence number plus vertex cover number is the order of your graph, this simple bound, then you get this upper bound, so that the packing chromatic number is at most the vertex cover number plus 1. And actually, so this is not so interesting, but more interesting is that, of course, the equality holds if your graph is of diameter 2. Because if a graph is of diameter 2, this means that you can use any color bigger than 1 only once. You cannot use color 2 twice because any 2 vertices would be at distance 2, but they should be at distance 3. And this is important because when you have equality here, then it's the same problem as the vertex cover number, and this will have consequences for the complexity. Okay, so this is what I just explained. Now let's go to the complexity issue. The packing coloring problem is just what would you expect. So you have given a graph, you have given an integer, and you ask, is the packing chromatic number at most k? Of course, no one is surprised that it's NP-complete for, in general, it's NP-complete for planar graphs. It's NP-complete already for k is equal to 4. This is also not surprising. We know the complexity of the usual coloring. It's already difficult for small chromatic numbers. And this is also not that surprising. So for chordal graphs of diameter at most 5. But this is already very interesting. I told you before, yes, now we have paths and even cycles, so we will treat the problem easily for trees. No, we cannot. We cannot, because this is a problem that is difficult already on trees. So this packing chromatic number is really an intrinsically difficult problem. It is already difficult for trees, where most of the problems, not all, I mean, we know some problems that are already difficult on trees, but this is another one. So this was due to Fiala and Golovach. Let me just give you a reduction. So not this one is quite tricky, but a reduction that shows that chordal graphs of diameter at most 5 are already a difficult case for the packing chromatic number, because here will be another instance when subdivision will appear in a natural way. And this will be also one of the problems that we will consider in the second part of the talk. So what we do, okay, let me just list you everything. The reduction will be from the independent set, and the construction is the following, described here. So you take your graph, then you subdivide your edges. Each edge is subdivided exactly once. The subdivided vertices, the new vertices, then form a clique in the new graph. So you make adjacent every subdivided vertex in the new graph, and to the original vertices you append enough pendant vertices. So you join how many k? Yeah, k leaves to original vertices. And this is a simple construction, simple reduction, and what you can show then that the packing chromatic number is bounded by k if and only if the independence number of this graph G is at least R. Now, what are the polynomial cases? So people were studying different classes of graphs. Here is a list of such classes. We already set path cycles, k is equal to and k is equal 3. That's what was explained before, and we said k is equal to 4. It's not polynomial. You can do it for split graphs in polynomial time. Then you can do it for graphs that have both bounded tree width and bounded the diameter. It was in the same paper where the NP completeness for trees was proved. And then are some special classes. They appear like very special classes, but they are not so special. I mean, these are special classes of trees, and we know that it's hard for trees in general, so it makes sense to consider trees, particular classes of trees for which one can do it. So these authors considered lobsters, So here it's what is lobster. Lobster is a graph that you can get it from a path, and then you attach some subtrees in such a way that the distance to the original path is at most 2. So you can do it for lobsters. And some bigger class also of split graphs, technical graphs, and also kind of partner limited graphs, which I also don't want to define here. The definition is here, but it's not so important. And also quite recent results, generalized theta graphs. Generalized theta graphs are graphs that are composed. You take a bunch of paths and you join them in an end vertex. So these are generalized theta graphs. Well, then people studied extensively also distance graphs. These will be infinite graphs, which are defined in the following way. So you take Z, Z is a vertex set of your graph, and then you take a set D, which consists of D1 up to dk. So these will be positive integers, and these integers just tells you how long jumps you make in your Z set. So if this set D, if this k is 1 and D1 is 1, this is just the two-way infinite path. So this is a really natural model on which you can study the packing chromatic number, how you spread your numbers all the way. And here is just a list what people could obtain, and this is kind of really telling you just for a feeling that this is far away from being a simple problem. So here you see, these all results are for the sets with only 2 jumps. In these first 4 theorems, you have the two-way infinite path, and then you add large jumps. So t here, for instance, if t is at least 447, so you have really big jumps all the way, yes, all the way both directions in the infinite path. And then they could prove that you can do it in the finite number with the finite number of colors, like 40 here or whatever here. And here are some other results when jumps are not 1 and something, but k and something, and here we have conditions. If k is odd or k is even or whatever, and t is large enough, then this can also be bounded. And there are also some upper bounds obtained by computer. So these particular bounds for smaller ones, not this one, but now here t is really small, you can do it with less colors. So if jumps are small, you would do it with less colors. Another couple or maybe 2 or 3 papers were dedicated to hypercubes. And in the seminal paper, the packing chromatic number of hypercubes was deduced up to dimension 5. And it was shown that asymptotically, you basically need exactly 1/2 of the vertices of the hypercube. So you cannot do better than using half of the number of colors. So the order is 2 to the case, and you need a little less than 1/2 of the colors for coloring. And recently, Torres and Valencia Pabon were able to deduce exactly the packing chromatic number up to dimension 8 and bounded also some others from below. And you really see that this is really like growing like 1/2 of the order. It's below, of course, but it's growing very quickly, the packing chromatic number. Cartesian products, finite and infinite, were also studied. There are several bounded cases, so here is the list. I will stop here. This is a recent half breakthrough. I would say breakthrough would be to determine exactly the packing chromatic number of the integer grid. So z times z, so we have an infinite integer lattice. And for this one, it was quite a long history. But now the bounds are between 13 and 15, and this was just published 2 months ago, a short note, again by using computer. And this can be said, in a way, can be generalized in the way that if G is any finite graph, and you multiply it with the two-way infinite path, then it's still finite. But on the other hand, as soon as you go to 3D, when you have three-dimensional lattice, you can show that the packing chromatic number is infinite. It's the same actually if you have only two-dimensional integer lattice and you multiply, you only take m layers of it. So you have infinite lattice and you take m layers of it in the sense of the lattice in the Cartesian product, and it's still infinite. And actually even in the product of two factors, when you take the first path to be of length at least 6, so this is just Pm of length 6, and H is the infinite hexagonal lattice. So now instead of taking integer lattice, you take your base graph hexagonal lattice. So you have 6 cycles all around your plane, and you make 6 copies of this hexagonal lattice, just add with Cartesian edges above, and this is already infinite, it's not bounded. First of all, before we pose the problem, let us have a look to the following situation. Suppose we have a packing coloring in which the color of each vertex is bounded by the diameter of a graph. So you don't want to have your colors too big, you want to have them not bigger than the diameter of your graph. Then such a coloring is eccentric. And now take ternary trees. So ternary trees are simply trees in which each vertex, so it is, well, in the limit, it's an infinite for regular trees except that the root is of degree 3. So you start with the vertex of degree 3, and then you add in each vertex 3 pendant vertices, and you fill your levels, and you continue like that. So up to level h, so th would be the ternary tree of h at least 4, and Sloper then proved, it was really, you see, 2004 paper, so it was, this result was basically proved before the concept of the packing coloring was introduced in terms of eccentric colorings. So he proved that these trees do not admit eccentric packing colorings, which means that if you consider this family of trees, then the packing chromatic number is not bounded, because if it would be, you would contradict this result, because if the packing chromatic number would be bounded by some constant m for any h, then you would just take this Tm, so TAH big enough, let's say m, you take this packing coloring and the diameter, so this condition will be fulfilled. So in the area of 4 regular graphs, the packing chromatic number is not bounded. That's why people ask the question, what about for the packing chromatic number of 3 regular graphs? Or more generally for subcubic graphs, so for graphs in which the largest degree is 3. This question was posed several times, at least in 2 papers. In the seminal paper already for the general case, in our paper, but actually due to Shkrekowski, the question was, what about cubic planar graphs? Is it packing chromatic number bounded for such graphs? And this is one of the breakthroughs I mentioned in the beginning. Just 3 months ago, archive paper was posted by Balog, Kostochka, and Liu, where the answer is no. And as you can imagine, they used probabilistic arguments. So what they proved is the following. So take any integer k at least 12, and take a girth of your graph to be at least 2k plus 2. Then they proved that almost every vertex, n-vertex cubic graph of girth at least g has the packing chromatic number more than k. Okay? Let me just give you an idea of the framework, how they proved this result. So this is just a framework, what they did it. The idea is the configuration model. The configuration model, okay, let me just give you the rough idea here. The configuration model is that you take ordered pairs of this set, so this is the set of first n numbers, n integers, And the configuration, so you have 3n such pairs. And what you want to do, what you say a configuration is simply you put these 3n vectors, I mean tuples, into pairs. In other words, you make a perfect matching between these two between these these elements of the set Wn. So you have 3n over 2 pairs. And all together, now you can consider all the possible matchings. You get 3n minus 1 factorial factorial, such pairings. And now you do, the trick is the following. What you do is you make a graph, multigraph out of this matching by simply forgetting the second coordinate. So you have the second coordinate, but you forget about it, and you will get 3 regular multigraph. So here you see each vertex will get 3 neighbors, but you can have loops because you can have a vertex with the first coordinate. I mean, 3, 1 can be adjacent, for instance, to 3, 2 in your matching, and this will be a loop then because you forget about the second coordinate. And you can have multiple edges. And then here now they come into the play G, this our set, cubic graphs. So the point is, of course, that this projection of this configuration is a 3 regular multigraph. And then you have these cubic graphs, and certain McKay, who's sitting over there, proved that then this configuration model allows you to prove results for your class of graphs, of your cubic graphs, with this vertex set. You reduce your problem to these configurations. So this is the model, and if you want to know something more about that, you just go to archive or ask Brandon about this model. But this is just an idea how they proved this result. Now, of course, as always with the probabilistic arguments, we have now we know that the packing chromatic number is not bounded in the class of subcubic graphs, but give me such graphs, okay? So give me a cubic graph that has packing chromatic number 100. Well, this is an open problem. So even with this result, there is a history, and it is still going on. I guess it will still go on, is what we say here, hunting for explicit constructions. So we want to have subcubic graphs with prescribed packing chromatic number, let's say 100. This is an open problem. We don't know any such construction. So for instance, in the usual chromatic sense, if you want to have a triangle-free graph with high chromatic number, you have Michilsky construction or whatever. Yes, you don't need probabilistic arguments like that one, that for any girth you have chromatic number at least big enough. But if you want to have a triangle-free, that's easy, yes? So first of all, we already set these Sloper's results. That in for 4 regular trees it's unbounded, but if you have a complete binary tree, so it means that you have every vertex of degree 3 except the root, which is of degree 2, then it's bounded by 7. And so one of the first results when we have cubic graphs is for hexagonal grids. So remember, we have a hexagonal grid, and if we have 6 copies of it, it's unbounded. So it is infinite packing chromatic number, but we have only hexagonal grid, then the result is exactly 7. So this would be a first big, let's say big exact packing chromatic number of cubic graphs. So another result would come from Sierpinski graphs. This would be a little bigger. So for instance, so this would be Sierpinski graphs of, I mean, these are base 3 Sierpinski graphs, there are others, but this would be subcubic graphs. And you see here, so the first few have packing chromatic number 3, 5, 7. And if you have n at least 5, then the packing chromatic number will be at least 8 or 9. So we have a bigger graph now with the packing chromatic number at least 8. But we have a better one. So this guy, let's call it G38. This guy has a packing chromatic number equal to 13. As proved by Gastineau and Tony, also very recently. And what is the proof idea? Well, the proof idea is, well, first of all, what is G38? G38 was independently discovered by several group of authors, and this graph G38 is smallest cubic graph, largest cubic graph of diameter 4. Known cubic graph of diameter 4, and it has order 38. That's why G38. What they did? Well, they did by a brute force search. They proved by computer that you can color at most 28 vertices with colors 1, 2, and 3. So independent set, 2 packing and 3 packing. The largest 1 to 3 packing is of order 28. Actually, this kind of idea, except not by computer, was also done in that probabilistic argument that the packing chromatic number is not bounded. But they were considering 1 to 4 packing. It turns out that the computation works if you do 1 to 4, and then you apply this configuration model. Now, what it means then? Well, why 1 to 3? Well, because diameter is 4. And since diameter is 4, any other color can be used only once. Which means that if 1 to 3 packing is of size, largest size 28, then any other vertex must receive a separate color, which means that you will need exactly 13 colors to color this graph. So in this paper, they asked the question so can we do it better? And let me show you a little better. This is the construction. But that's really like that it's working only in this setting. So you take now 2 copies of G38 and you subdivide one edge once. So X prime is the new vertex, but the rest is G38. You do the same here. So this is another copy of G38 with one vertex subdivided, and you add this edge between these 2 copies. This will be again subcubic graph. Let's call it G78. It has 78 vertices now, and it is subcubic. And what we can prove is that the packing chromatic number is at least 14. Probably it's 14, but we are now happy to show it's at least 14. So what is the idea? Well, suppose you have a 13 packing coloring. You cannot have a smaller one, of course. So suppose you have a 13 packing coloring of this one. And then part of this argument, again, needs a computer. So the computer is needed that this G38 prime, when one edge is subdivided, requires exactly 12 colors. Now, the diameter of this guy is at least 12. And why is that so? Well, under this assumption, well, you just consider what happens. So suppose you have 13 coloring. There are 2 possibilities. So you have one vertex of color 13 here and one vertex color of 13 here. Well, you're happy because they are distance 14 at least. If you have color 13 and 12 here, then you must have a color 12 here or here. So the point is that if you, among the first 3 colors, 13, 12, and 11, you cannot miss 2 colors on one side. Because if you miss 1 color, 2 colors, the largest color would be shrinked down, and you would get a contradiction with what we have. So basically, you have at least one of these colors on both sides, and then you take these vertices of the equal color on both sides, and you get that the diameter of this guy is at least 6. Of this one, G38 prime. But then this would mean that G38 would be of diameter at least 5, which is not the case because we know it's of diameter 4. Another very recent result about subcubic case are the duals of, well, are the outer planar subcubic graphs. So what is the weak dual? Weak dual is simply the usual dual, but you don't consider the outer phase. And the weak dual of two connected outer planar graphs are trees. And if you have some special conditions on this weak dual, then you can bound the packing chromatic number of outer planar subcubic graphs. This is then this result. So this was also just posted on arXiv, and this result is then related to the question of before about cubic planar graphs. So these are some bounds for the cubic outer planar graphs. So this was one thing, and another thing is the problem about subdivision graphs. You recall that subdivision graphs already appeared a couple of times in my talk. So if you subdivide vertices, edges once, the distances are multiplied by 2 in the original graph. And the subdivided vertices, the new vertices, can always be colored with 1. So here is a question posed by Gastineau and Tony. So the question is, suppose you have an arbitrary graph G, and now arbitrary subcubic graph G. And now you subdivide each vertex, each edge once. So this is the graph S of G. The question was, is it true that the packing chromatic number is not more than 5 in this case? Which is quite in contrast with the fact that in general the packing chromatic number is unbounded on subcubic graphs. But if you take subdivision graphs, then the question was, is it at most 5? And actually, now we don't only ask this question, but we have this as a conjecture. We pose the following conjecture. If you have a subcubic graph, then the packing chromatic number of its subdivision graph is less or equal than 5. Here is some evidence that this might be the case. Well, first of all, you can reduce your problem just to cubic graphs if you want to prove the conjecture, because every subcubic graph is a subgraph of a cubic graph, and then you can just use your coloring from the cubic graph and going down to the subcubic graph, because you just have bigger distances than when you remove some edges. And you also can restrict to three chromatic graphs. So we connect this now to the usual chromatic number, because for the two chromatic case it's known that it's true. So from the seminal paper that it's actually 3, so definitely less than 5. And of course the only 4 chromatic such case would be K4, and this is also the case. So the conjecture really is asking, is it true that if you have a 3 chromatic cubic graph, is it then the packing chromatic number of its subdivision at most 5? And the conjecture, you really need these two assumptions. You cannot just go to 3 chromatic graphs. So if you take a complete tripartite graph, K, N, 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 this is 3 chromatic, of course. But the packing chromatic number when n goes to infinity also goes to infinity. So if you have only 3 chromatic graph, but bigger degree, this will not work. Now a little general framework, which is also interesting and very useful in this context, is the so-called A1 up to AK packing coloring. Now in this case, you prescribe in advance the packings you want to have, and you can repeat the packings. So for instance, here, if you would say this all AIs would be 1, this is the usual coloring. And you can have here, for instance, 1, 1, 3, 7, whatever you want. But of course, you don't want to make gaps, but you can repeat the color classes or the packings. So this would be A1 up to AK coloring. So k-packing coloring, the usual coloring is simply if you put here integers from 1 to k. And Gastineau and Tony proved that if you have a 1, 1, 2, 2 colorable graph, then the packing chromatic number of its subdivision is bounded by 5, which is not difficult to see, because if you have this thing here, then again the subdivided vertices over there can be colored with color 1, and vertices from these two classes can be colored with 2, 3, and vertices from these two color classes from these two packings can be colored with 4 and 5, because the distances multiply in the subdivision graph. So to deal with this thing here, it's good to understand 1, 1, 2, 2 packing colorings, and we can actually characterize when a graph is 1, 1, 2, 2 colorable. It's a simple characterization, so you want to have a partition into 3 sets, such that 2 sets are independent, and the third set, V1, is a bipartite graph in the square of the graph, where the square of the graph is the graph where you make adjacent also vertices at distance 2. What is a generalized prism? So what was the aim? So you can now consider cubic graphs, and then you have partition of cubic graphs into cycles and perfect matchings. Yes, you have 2 factors. So what is a generalized prism? A generalized prism is simply you have 2 cycles and a perfect matching in between. For instance, okay. And we could show that if you have a generalized prism over a cycle, of course, which is not the Peterson graph, then any such guy is 1, 1, 2, 2 colorable, which means that for any such guy, the conjecture is fulfilled. A generalized prism over cycle has packing chromatic number at most 5. These are 2 examples of such generalized prisms, and this would be the 4 packings. So 1, 1, so 1, 1. So these are 2 different, 1 and 1 prime. These are 2 different independent sets, and 2 and 2 prime would be such. So we have this guy here or this guy here, and for all these we can show it, but not for the Peterson graph, because it doesn't have such 1, 1, 2, 2 coloring. But this is a packing coloring of the subdivision of the Peterson graph with 5 colors. As you can imagine, this was also found by computer, because anything natural you want to try to do it, like with trees. There are several things you want to do it, and you think it should work for the packing coloring for trees in a natural way, like dealing all leaves with the same color or whatever. Or here, yes. So what is the natural thing to do in the subdivision graph? Well, to color every subdivision vertex with color 1, because this is exactly the largest independent set, and they are precisely at distance 2 and so on. Yeah. So what better can you do? Well, you can. If you do that, you actually can prove. Okay. So now first of all, the Peterson graph was the only exception, and by the way, then this theorem really gives you a new characterization of the Peterson graph, if you want to look at it like that. So the Peterson graph is the only generalized prism over a cycle that is not 1, 1, 2, 2 colorable. Okay? So here we prove that everyone is, the Peterson is not, so we have a new characterization of the Peterson graph. And actually it turns out, so here we have word strange packing colorings. It says that this phenomena happens in general. If you have a graph that is not 1, 1, 2, 2 colorable, but the subdivision is 5 packing chromatic number colorable, then you must have a strange coloring, in the sense that every coloring that is optimal in the packing coloring will be such that a subdivided vertex will receive a color which is not 1, like here in the Peterson case. So here we have 3, 3, here 5, and it works. And it doesn't work if this all would be 1. And finally, we have a stronger result also. which says that you can find 1, 1, 2, 2 coloring not only if you have 2 cycles and the perfect matching in between, but the factorization can be such that you have 1 cycle of half of the order of a graph, and on the other side you can have any number of cycles, except that only 1 cycle can be of length 5, and a perfect matching in between the long cycle and the short cycles. And of course, we need to exclude this condition, at most 1 5 cycle, because if you would have 2 5 cycles, then you would come back to the Peterson graph, for which we know we don't have such a situation. Let me briefly just summarize some of the problems that we saw already during the talk, and add a couple of more. So first is this very nice question. So determine exactly the packing chromatic number of the integer lattice, of the square lattice. We said now it's between 13 and 15, so we only have 3 possibilities. Is it 13, 14, or 15? With respect to grids, this I think is also quite an interesting problem. We said that if you take 6 layers of the hexagonal grid, so you take hexagonal grid and you take 6 levels of it, then the packing chromatic number is unbounded. But we also know that we only take 1 layer of the hexagonal grid, then it is 7. The packing chromatic number of the infinite hexagonal grid is 7. Now the question is how many layers you need to take that you jump from the finiteness to the infiniteness. So we know it's somewhere between 1 layer and between 6 layers. We know that the problem is difficult on the class of trees, but what about if the trees are of bounded degree? So is the problem then still difficult, or is it polynomial if the trees have bounded degree? Related to the second part of the talk, we also don't know the complexity of the cubic case or subcubic case, and the guess would be that it's also difficult, but the proof would be welcome. With respect to the explicit construction, this is also, I think, an interesting problem. So we know that almost all guys have large packing chromatic number in the for cubic graphs, if girth is large enough, but we have no explicit constructions. It would be very interesting to have such explicit constructions. And finally, this conjecture that every cubic every subcubic graph, its subdivision graph has packing chromatic number at most 5.
Thank you very much, Professor Klavzar. Any questions, anyone? We have plenty of time.
You mentioned that one of the motivations for this idea of packing chromatic number was from coding theory. There's a connection between coding theory and that concept. And you gave some bounds on the packing chromatic number of the n-dimensional cube, which is really the cube over the binary alphabet. Now you can replace that cube by a cube over the q-ary alphabet, 0, 1 up to q minus 1, okay, which certainly has importance in coding theory. And so I'm wondering, one, whether or not you've ever looked at that question, and two, the question that you looked at relative to the n cube was using the Hamming distance. Now there's also the Lie metric, which is important in coding theory, and presumably one can investigate some of this with regard to the Lie metric.
No, I'm not aware of any of this investigation, but it's definitely interesting. So in our world, in the world of graph products, we would really then consider the packing chromatic number of Hamming graphs, what we call them Cartesian products of complete graphs. And for the Lie matrix, this would be the packing chromatic number of Cartesian products of cycles, if I'm not wrong. Yeah, these are precisely Lie codes, yes, if you take Cartesian products of cycles. And I don't know that anyone would, but it would definitely be interesting. In fact, I think I've seen something on arXiv quite some time ago, but never appeared this paper. It was something with Hamming graphs, but I don't know. So maybe someone did. So these guys from Argentina, they were mentioned in this talk. So maybe they did some touch into Hamming graphs. So these alphabets of order more than 2. But that's all.
Any other questions?
Hello. There is the case where you can get graphs from Voronoi cells of various sorts of bodies. The one that I'm most familiar with is you take a finite set of points on a sphere, say the unit sphere or the unit hypersphere or whatever. You take a Voronoi tessellation and you take its dual to get a Delaunay triangulation. I was just wondering whether that sort of configuration has been looked at from this sort of context. So it's new.
No, not at all.
So I guess we can thank Professor Klavzar again.